Hi there folks, my name is Natalie and I am a member of Gauntlet Cohort 2 and I am really excited to bring the LAPACK project to a close. LAPACK, for those of you that don't know, is a comprehensive software library that is over 30 years old and it is written mostly in Fortran and C. And this week at Gauntlet was Enterprise Week. So it was the week where they challenged us to take a large existing enterprise code base and see how AI could do at adding new features. So I chose LAPACK. And LAPACK is a core code base that is used by lots of different overarching code bases and programs like NumPy, SciPy, MATLAB, if you've ever heard of those. They all call on LAPACK for its low-level matrix multiplication subroutines and many other algorithms, some experimental, some core, and well-developed over decades. But this is the basic premise of how external third-party libraries use LAPACK. In essence, there is a core application layer, which are the actual Fortran and C++ applications. Then there's LAPACK E, which is the actual C interface layer, and C BLAST, which is the equivalent interface layer for the BLAST routines. And these two core packages talk to each other and give us the matrix multiplication functions that we all know and love. So what I did this week was I tried to add a new subroutine, and I did. So now LAPACK has a new variant, which is Alpha Tensor's 49 operation matrix multiplication algorithm, which is faster than the default 64 operation 4x4 matrix multiplication algorithm. So in theory, this should save us about 10 to 20% in terms of the operations that the computer would actually need to do to get our full matrix multiplication output without compromising precision or performance and, well, ideally improving performance and speed. This is all theoretical, and as you can see, the research spans a long period of time. People have been talking about matrix multiplication for a very, very, very long time. So this is the first time I'd ever heard of it being applied to LAPACK, and so I decided to do it. So to be compatible with the code base, I put all of my documentation and most of my implementation in this modernization subfolder, but I also put the raw algorithm in the variant subfolder. However, I want to just jump in here and show you some of the results because I think that's a little more fun than just looking at the raw Fortran code. So what I did was I separated my implementation of the algorithm into phase 1 through 9, and phase 1 was just, can we even translate the Python into Fortran? Turns out we can, and AI can help us. And then second, does it work? Turns out it does, and it does with machine or professional level accuracy. We were about 1 times 10 to the negative 15th in terms of accuracy, so within a floating point error. But we were able to get very accurate results while still replicating a new Python algorithm in Fortran. But then it wasn't fast enough, so it was much slower than the default DGEM algorithm, and obviously we're competing with the default matrix multiplication algorithm, so I decided to go through multiple testing phases. In general, we did this, which was to compare on a CPU what the speed and the performance gains and the accuracy would be between DGEM Alpha, which is the Alpha Tensor implementation, and DGEM. So I tested about 488 different matrices and separated into these general 12 cases: identity, zero, mixed sign, random, dense, diagonal, all the other stuff. For mathematicians, this means something, but for those of you that aren't so refreshed on matrix multiplication, it's different kinds of matrices. And in essence, we saw anywhere from 1 to over 4 times faster as we replicated and reproduced our results. These speed improvements were actually well seen throughout all of our testing. But for some kinds of matrices, we actually saw slower results, especially for sparse matrices. And this is pretty expected because it's challenging for this kind of algorithm. But I did publish all of my results in a BrainLift subfolder on the repo on the branch if anyone wants to know about my detailed implementation and how I believe that people could use this. But after doing these initial optimizations, I decided to do much more. So here in summary is the latest phase of optimizations. I'm fairly competitive, so I was trying to beat out the DGEM algorithm at every stage. So what we ended up doing for our next phases of optimization was common subexpression elimination, which involved just caching matrix elements to reduce redundant array calls. And this sped us up quite a bit and reduced our lookup call numbers. Then we did compiler optimization for CPU, so we can actually, in the Fortran code, detect the kind of compiler that someone is calling the code from, and add compiler-specific directives for running each of the matrices, which saved us a little bit of time. Then I found this new algorithm, which was called the Strawson alpha tensor. Well, I call it the Strawson alpha tensor hybrid. But this added support for 8x8 matrix multiplication, which reduced the total number of operations from 512 to 343. And this also extended our default 4x4 matrix multiplication algorithm into essentially any kind of algorithm. It's not mentioned here, but I also implemented block-based subdivision. So now any matrix that is 16 by 16 and up can be subdivided into a matrix and called with alpha tensor. So any matrix with dimensions that are divisible by 4 and it's a square matrix can apply this algorithm now. Let's see. So after this, I thought that's great for CPU, but what about GPU? Because that's where the real performance gains would be seen. So I actually implemented an OpenCL GPU implementation, and basically I wrote a kernel. And the kernel is, I'll show you right now, actually. Let me go pull it up. So here is our kernel implementation. We had the original alpha tensor algorithm here, complete multi-algorithm optimization suite. So this includes the Strawson, the blockwise alpha tensor algorithm that I was telling you about, which is for subdividing larger algorithms, and a bunch of different other floating point. I did so many things to make this fast. I think in the end we were able to get about a 7 times speed increase on CPUs after all of these optimizations for some of those high gain matrix types. But again, this wasn't enough, so I decided to write my own kernel. So now there is a simple 4x4 matrix multiplication alpha tensor kernel, which you can call from a GPU, and it will run the alpha tensor algorithm. So yeah, it's not perfect. It still shows a couple of errors for larger matrix types, but it does have perfect accuracy for most. It was 12 out of 14 tests that we did with different matrix types that it passed. And if you go on my branch, you can read the full report. But now there is a kernel for folks to try this out on their own GPU. And that's what I ended up doing. I created a Terraform script that goes ahead and provisions these resources for you, creates an S3 bucket for you to put your results in, and provisions a GPU testing instance. As you can see, it's called Natalie Alpha Tensor GPU instance. But it was really fun to do this and experiment with rapid Terraform, tear up and tear down architecture and see how the GPU would perform. As I mentioned, we got mixed results, but that's real science, folks. And this does exist on a branch now, so if you would like to go play around with my kernel, you can. The last thing I will show you is the Python demo script that I made for everyone to play around with. So here is the Docker command that I run to run our Jupyter Lab script for any scientists that want to play around with this. I'm in the wrong directory, so let me fix that. Great. So what I will do is I will clone the repository and make sure I'm on the right branch in this case. The PR will get merged in, but the build pipeline takes about 25 minutes. So in about 25 minutes, you'll have it all merged into main. But I will run the Docker container and expose port 8888 to the LAPACK Jupyter implementation, and then I will mount the default working directory into the workspace folder. And now we're running. So I will go ahead and navigate here. Great. So if I go into the modernization implementation subfolder, oh, whoops, it's one level up, demo, there we go. I can open up the Alpha Tensor Python demo. There will be some performance losses as you run this demo, because essentially what we're doing is we're taking the raw Fortran run and applying a Python wrapper to it, but that's also explained in the demo. So what this script will do is it will check if you are in a Docker container, set up all of the necessary dependencies for the demo script to run, and then it will check if you need to build the Alpha Tensor library, which it will do for you if you do. And then it will create an Alpha Tensor interface for you to talk to the Fortran raw dgem alpha algorithm. It will be ready. And then you can run a quick validation test by doing some matrix multiplication yourself to see if Alpha Tensor is running. And then we get into the meat and potatoes of everything, which is the performance comparison. So here is the pure algorithmic performance improvement that we got for all of these matrices. So as I mentioned, after all of our optimizations, we actually saw a higher than 1 times average performance improvement. It was closer to 2.6, but it does suffer a lot with the Python interface. So that is something that is an open bounty to the scientific community, is making a better Python interface for this thing. And here are the results visualized. Here is the native Fortran performance on a CPU, and here is the actual performance through the Python interface. I'm sure that there are optimizations and potentially a low C wrapper that you could use to make this faster. We saw comparable results on the GPU as well, but as I mentioned, there were some things on the GPU for which it was much slower. But on the GPU, we did also see much better floating point precision. We got up to 10 to the negative 15th on the GPU, so that was very nice. But in conclusion, I set out to prove that you could refactor or add to an existing enterprise code base with lots of old code, and I did it. And I did it with Cursor and AI. This code is out there for anyone to use. In some situations, it performs much better than the default dgem algorithm, and it is applicable to any matrix divisible by 4. So any ML people out there, feel free to play with this code. It's open source and available for anybody. So thank you. I had lots of fun, and I'll see you next week. Bye-bye.